are we ready for the second lecture? All right, so let me introduce you to our next speaker, Mr. Omar Hussain. I hope I have pronounced your name correctly. Mr. Omar Hussain works at the Mohammed bin Rashid Space Center, and he will be speaking about UAE's Mars mission. So I did not receive Mr. Hussain's bio, but I've done, while we were all taking break, I've done a little online searching, and I found out that he's the lead mission designer and navigation engineer. Am I correct? And so apparently you have a background in computer engineer, and you led Hope Probe's Monte Carlo simulation, so you must be a genius. So with that, the floor is yours, Omar.
Okay, so hello everybody. Yeah, I'm genius in no means. I'm actually, when I started working for the Emirates Mars mission, just to give you a brief introduction about myself, I was just fresh back from South Korea working on KHALIFA-SAT on the attitude control subsystem. And once I arrived, they gave me an opportunity to basically work on the Emirates Mars mission, and things went well, and I ended up leading the mission design and the navigation efforts, and currently I'm working on the navigation, and of course we're doing mission design work for some extended science stuff that you will hear about in the future. Where we're doing some mission design work for that, and I thought I would give you like get straight to the point and show you a quick video of a simulation using AGI software. What do you call it, SDK, in order to basically show the mission from mission launch to arrival at Mars. Let me share the video screen. Sorry. Okay, so Zoom does not let me share full screen. I think it's some kind of protection against piracy or something. So let me just remove the full screen from the video. Yep. And share it. Okay. So yeah, as you can see, I'm pretty efficient when it comes to working. I made this I made this simulation in 2016, and I've been using this simulation since then in order to basically explain the whole Mars mission to everybody from that time. So we'll start with the launch. So basically we chose to launch from Japan using H-2A, Mitsubishi's heavy industries rocket. And that is due, of course, to we looked at the launch window and the arrival time. Since how does my work start as a mission design engineer? Basically, they tell me, okay, we have these scientific instruments. We want to get to Mars at that period. Could you please design us the mission? And then we work from there. So we work backwards. So we knew that we want to be at we want to be in Mars in February of 2021. So we went backwards 7 months basically, and we saw where the position of Mars is going to be. And from there, of course, we calculated what we call C3. C3 is basically the amount of power that is required in order for us to get from Earth to Mars. And we looked at different candidates for our launch vehicle, and from them, of course, SpaceX. We looked at SpaceX, and we looked at Soyuz, since we launched with them in the past, and we found that Mitsubishi would be the best choice between the three. So starting the simulation now. Just a quick 4-minute simulation. Yeah, so we launch. As you can see, when it turns yellow here, the orbit, this shows us that we went into an intergalactic orbit. So this is when the second stage of the rocket started firing, and basically we left Earth's orbit. We were in an orbit around the Earth, an orbit of 400 kilometers altitude. We did a huge maneuver in order to get our eccentricity greater. That's too much to detail. Okay, in order to go to an orbit that is actually that escapes Earth's orbit. So we're going from one orbit around the Earth to an orbit around the Sun, and then an orbit around Mars. Since spacecrafts have to go in orbits, we can't fly straight there like in the movies, sadly. Well, this is when we conducted the first contact. At the time of the simulation, we actually planned to have a space station in the UAE, ground station, but that was not possible due to some reasons. But yeah, as you can see from there, that we took into account that there was going to be a space station in the UAE. So then after we launch, we go into our interplanetary orbit. So as you saw earlier, if I just go back 10 seconds, sorry. Yeah. So what we do is we do our trajectory correction maneuvers. So why do we do that? Well, when we launch from Earth, in order to get to Mars, we don't actually point at Mars directly. We don't want our spacecraft to be in the sphere of Mars. Why is that? Well, because of planetary protection. You see, when it comes to doing deep space missions, especially Mars exploration, we want to make sure that we do not contaminate the surface of Mars, in any situation possible. So the situation that we took into account is what will happen if basically we launch our satellite and it's dead. We cannot do any maneuvers. So we'll crash straight into Mars if we do not actually launch away from Mars. So that's why when we start, we usually what we call it is a launch bias, and we launch a little bit away from Mars. And then what we do is trajectory correction maneuvers, which actually corrects our trajectory in order to get us in an orbit that gets us into a point that is 500 kilometers from the surface of Mars. So we're going to see the trajectory correction maneuvers now. So we have planned in advance for 7 or 8 maneuvers, and 3 of those were contingency maneuvers in case we get there and where we do the navigation, and we find out that we are actually not in an orbit that's going to get captured around Mars. So that's why we have three spare maneuvers, which I mean, we did not conduct them, so that means the launch was really good. And our first correction maneuver was actually really good. So we actually did 2 minor maneuvers, which is TCM2 and TCM3, in order to get to Mars. So once we get to Mars, so these are all contingency maneuvers that we have developed in advance. So now that we're getting into Mars, okay. So we're going now from an interplanetary orbit, which basically means an orbit around the sun, to an orbit around Mars. So we need to basically lose all that energy that we have right now from launching from Earth and slow the spacecraft down in order to get captured by Mars's orbit. So that's what we're going to do here, basically. What we call this phase is the Mars orbit insertion. We call the maneuver the Mars orbit insertion maneuver, and it's our biggest maneuver. It actually uses around a ton of fuel, and the spacecraft carries 1.5 tons of fuel. So you can actually, not 1.5 tons actually, it carries around 1,200. So yeah, you can see that it's actually a very big maneuver. Like it's our biggest maneuver. I might have gotten the fuel values wrong. I'll double check those, but it was something around that. So we use actually 950 kg of fuel to slow down the spacecraft over here. So what we do is, if you look at on the top right, you can see here orbital elements. What we call those orbital elements. So similar to the ones around the Earth, we actually we use the same orbital elements, but for Mars itself. So what I want you to look at here is, if you see on the top left, how can I show the? There's no need for the pointer. Actually, it's just on the top right. Sorry, you'll see Mars eccentricity. So this is actually the thing that we care about the most. Since what this tells us is, right now we are in an eccentric orbit. Highly eccentric orbit actually around Mars. This is a parabolic orbit, which means that we're not going to get captured if we look at it now from Mars's perspective. So right now what I'm doing is I'm looking at the simulation from Mars's perspective, the spacecraft itself. So we're looking at those elements. Once our eccentricity goes below 1, it means that we are in an orbit that is elliptical. It means that we are in an orbit that basically we are in orbit around Mars itself. So yeah, so you could actually look at the values right here on the top right. Yeah, once we go below 1, we're like, okay, we're going to get captured. We know we're going to get captured. So here we do our Mars orbit insertion maneuver. If I can pause this for a second. As you can see here, also we're in a really awkward position where we actually right before the maneuver ends, we don't have contact with the spacecraft. So that was a very interesting time in that, okay, we're waiting for 15 minutes while the spacecraft is behind Mars, and then for the two-way light time in order for us to know, to get the message that, yeah, the burn was conducted properly. So yeah, then we got the message, the burn was conducted properly. And then of course the navigation work started. We quickly started doing analysis to make sure that we are not in an orbit that's going to crash us into Mars. And we gave them the safe sign, and then we were like, okay, we're now in our capture phase. So the capture phase, we stay in our capture phase for like a month. The capture phase actually, here we're going to just check the health of the satellite, since we just did a huge maneuver. We used a ton of fuel to get basically to Mars. So we're going to quickly check the subsystem, check the spacecraft health, everything's okay, before we actually go into the science orbit. So the capture orbit is just the initial orbit that we use around Mars in order for us to basically get captured by Mars's gravity. So as you can see, this orbit is really eccentric. Our periapsis, our lowest point is 500 kilometers from the surface, and our highest point is 40,000 kilometers. Here it's 30 kilometers in the simulation, but it's in real life it was 40,000. So yeah. So yeah, what we did here, we planned actually for 3 maneuvers, what we call transition to science maneuvers. However, we did 1 maneuver and we found out that we were in a proper orbit around Mars, so we do not require any more maneuvers. So I will show you now why the capture orbit is really is an orbit you don't want to stay in, since it's highly eccentric, like I said. What that means is that we get very close to Mars. So Mars's gravity affects us and actually slowly starts perturbing or changing our orbit into a different orbit. So of course we take that into account, and in this simulation, we're going to show. We planned for 2 months, actually a 2-month period to stay in the capture orbit, but we saw that everything was okay and we can actually transition into science. So we did it in just 1 month. So that was great. And the transitioning phase here, you're going to see it's divided into 3 maneuvers, but we did it in just 1. So we just did TSM1. So basically, when we were at the highest point, which is at 45,000 kilometers, we want to increase the altitude of our lowest point to around 20 to 23,000 kilometers. Why? Since that's what our payloads want. So I'll speak more about the payloads as we go into the science orbit. So here we just did the first maneuver and we went into an orbit, and turned out that that orbit was great, and all those Monte Carlos that you mentioned earlier were for nothing. Yeah, I mean, but you have to take, of course, probability into account going into space, as you don't know what happens. So that's why for each maneuver we have to do what you said, Monte Carlo. I don't know why they actually captured that in the articles. That's such a small part of the job. That's just running simulations and making sure that we hit the right target. So after TSM3, so we did it, this transition to science maneuver. So we did it in 1 maneuver instead of 3. We planned for 3. However, after we did the first maneuver, we did the navigation. Turned out everything was great. So yeah, as you can see on the left, that's our science orbit. And now we'll look at Mars from the view of the spacecraft itself. From the orbit itself. So this is the orbit coverage, as you can see. So we chose this orbit in order to get full year coverage around Mars, full Martian year coverage. That's important. The Martian year is 2 Earth years. So we wanted to cover the whole surface of Mars throughout all of the seasons, throughout all of the lighting conditions, throughout a whole Martian year. So that's basically the goal of the mission, the big goal in general. So yeah, we did that and we got into the orbit, and right now we're conducting our science and observation data and our observations, and everything looks great. And we have released some new findings, like the localized auroras and some other findings on I think the science team released on Instagram. They're more knowledgeable than me regarding that. My job is just to get the spacecraft there. Yeah, so they were just showing the, yeah, so these are our partners. We work together with Advanced Space, which is a company that was started much like Satrec, I would say. It was spun off from Colorado University. So that's interesting that the first place I want to work for is actually, I was working in Advanced Space at the time. So the first place I want to work for is actually doing the same thing that Satrec did years ago. So that's it for my presentation. If you have any questions, if you want me to go back to the video, show anything, please go ahead. And yeah, that's it for the video. Thank you very much.
Oh, thank you, Omar, for a very genius presentation, I would say. So while we wait for questions from the students, I actually have a question myself. How does it feel to be part of a Martian mission? No, how does it feel? Because Korea hasn't, we haven't gone to that point yet.
I want to say, like, give you all and say, like, oh, it's the greatest feeling in the world or everything like that. But to be honest, it felt the same as launching any launching an Earth satellite. It actually, it's actually the same feeling exactly. Launching an Earth satellite and launching an interplanetary mission. Yeah, getting into Mars. We have other events, of course, like, oh, we launched, okay, we went into our interplanetary orbit, we arrived at Mars, now we're at Mars. So we have these milestones in order to talk about, but as engineers, to be honest, and as programmers and as a navigator, it's not that much of a different feeling, At the time, of course, everything is great, and you are lucky to get into Mars, since you can say the chances are 50-50 if we take older missions into account, but we cannot take that into account, of course, since that's the past. But yeah, so we got lucky, and we're pretty happy with it, I would say. I see a question from Dr. Kim.
Right. Were you a bit nervous that something that you have worked on might go wrong?
Oh yeah, definitely. I was. I mean, if you look at, if you watch the video when we arrived at Mars, you see Omran. He's like waiting for the signal in order to arrive, and you hear somebody screaming in the background that we got there, because I'm the first person to get the signal that, yeah, we're in a proper orbit around Mars. We're not going to basically go into an interplanetary orbit and wait 4 more years in order to get back to Mars again.
Right. Okay. So while we were chatting, I think we got some questions from the students. The first question was in Korean, so let me translate this for you. So why did you go to the Mars before going to the moon?
Okay, so I mean, people keep asking that question, like, why did you go to Mars before going to the moon? Well, there's a lot of interesting science to do around Mars, and to be honest, the moon is, by all means, I'm saying we haven't lunar missions and all of that, and we have a lunar rover launching next year, hopefully, and we're gonna land there. But we chose Mars because of the we could provide more for the scientific community. We can provide more science data to them. If we went to a Mars mission, if we did a moon mission, we're basically just orbiting a dead rock. There are already enough satellites, and they already did all of the interesting science, discovering the ice and all of that. And what's the next best thing to do on the moon is to land. So that's what we're doing next. We're sending just a small rover.
Right. Thank you for answering that question. And there's a second question also in Korean. So it says, why did you use the Japanese launcher?
Okay, so if I go into, okay, I will try to not go into a lot of that. So what we do is when we launch a mission, we want to have an ample launch window. So what we mean by that is that we want to have a number of days, like let's say, what we want is basically 20 days by NASA standard, in order for us to say that, okay, we can launch, our mission is pretty safe. Like we have 20 days to launch. So what we did is when we looked at the arrival and the launch using the C3, which is shows the energy of the launch vehicle itself. When we did the math for the 3 launch vehicles and for the arrival time that we wanted around Mars and for our orbit, we saw that H2A Mitsubishi Heavy Industries rocket actually gave us 21-day launch window, which was perfect for us. When we looked at the other ones, they gave us a smaller launch window, and of course, other things go we have to take other things into account. Of course, some of them would be political. You cannot launch an American rocket from Russia, you know. Some of them would be financial, so we'd have to look at basically the cost itself, since we have certain cost. And H2A fit us perfectly for that.
Right, thank you. Apparently, you know, a Korean launcher was not available at the time. So that that could not have been an option. A third question, right? Maybe in the future. A third question, again from a Korean student, from Dohyung Kim. I guess it's a female student. She says, hello, and thank you for a very interesting lecture. I also major in computer science, computer programming, and became interested in rocket engineering, and wants to be involved in launcher development, especially in like simulation and software development. But she wants to know where she should get started in terms of developing simulators, and what kind of software programs did you use, and the language that you used for the programming, and is also asking for your email address, if you can share with us.
Definitely, I'll drop in my email address in the chat. If you have any further questions, please forward them to me. So I'll start by answering the questions. So the best place to get started for everybody is there is a software called General Mission Analysis Tool, or GMAT. I'm going to write it down in the chat with my email. So you can download this software. It's an open source software, and it basically does everything that our very expensive software does. And you just have to basically work on the models itself and do them, like really build a good gravity model in it, like just adjust the gravity models and other models in them, and you can actually get as good results as we are getting right now. So I'd say general mission analysis tool. So for me, when it comes to, as a computer engineer, of course, my favorite language is C++, but I never got to use it in space for some reason. Everybody uses C#. So I programmed with C#. Basically our models that we needed, and all the solar radiation pressure model and other models. What I mean by models is basically what forces affect the spacecraft as we get to Mars. Since when we're traveling for 7 months, even the photons that are coming from the photons, particles coming from the sun, they actually change your orbit. So that's what I mean by solar radiation pressure. So all these models we built in C#, but I'd say mostly. Like once you get into a professional environment, unless you work in embedded software, which is the software of the spacecraft itself, you're going to use higher level languages. So expect to use a lot of Python. For me, for instance, I use GMAT a lot, the General Mission Analysis Tool, for my Monte Carlo analysis, specifically, since it's a very light software and you can launch it using, what do you call it? Using kernels in both, using the terminals in both Windows and in Linux and in Mac. So you have a lot of choices, but basically you need to know a high-level language. So if you know Python, Julia, or I'd say even MATLAB, you can actually do all of the work that we are doing at the moment. You don't need any really, I'd say, embedded software knowledge in that.
Right, thank you. So if you could drop your email address, and I'm sure that students will have more technical questions following what you have just explained. The next question is from a student called Choi Sung-uk, another Korean student. He has asked, you said that there were 6 120 Newton engines on board, and what was the development process like?
Sorry, what was that? The question again?
The question.
Maybe I can read it in chat.
120 Newton engines, 6 of them. Was that for? Did you have a propulsion on your Mars spacecraft?
Yeah. So I'm not actually working with the thruster team, so I don't know the exact details, but we're using six thrusters, two thrusters coupled. So we actually look at 3 models of thrusters. So we'd say we use 3 thrusters, thruster controllers, but 6. We have 6 thrusters coming out from the bottom of the spacecraft itself. And I have to check the exact values, but I'll give you the exact values of the engines that we used for launch exactly, since I don't know how many per second it was exactly. Sorry, I don't know the exact values of the engines itself, but I know the delta V's we used, but that's no help here. So I'll email you the engine details. But yeah, you're correct.
Right, thank you. And there's one last question from Song Min-soo. It's in English, but I'll just read it anyways. He said, I'd like to ask you a simple question. What was the most difficult part of this process, especially when it comes to predicting the path? I guess so the process of mission designing and analysis. So especially when it comes to predicting the path, it seems like there have been a lot of efforts and technologies to claim that.
Yeah, so the hardest thing is, as you would say, is basically, for me, I would say it's navigation more than mission design, since mission design was an ongoing work and we were working on the mission. And to get actually to an accurate point on Mars, what you need is a good launcher. Since the math and all of that, you can actually do it with open source software. Like, I'm going to write down the software details and everything over here. So you can use that. What do you call it? You can use that tool, but I'm sorry, I read the question and I lost my train of thought with the previous question. So yeah, the most difficult part of the process, I'd say it's navigation more than mission design, actually, since we're using radio data, which is unintuitive. Since I worked on Earth missions, I worked with Satrec in Satrec for a few months, actually, on KOR-UAE on the ADCS, and we use GPS for navigation. But once we get into deep space, then we have to use radio for navigation. So things actually go backwards, and you have to do math using like Doppler equations and two-way ranging, and then go into delta Dor, which is I'd say one of the most difficult problems we had to solve, which was the delta Dor problem. I'd say that one was a very difficult problem. It's basically where we want to get the position of the spacecraft itself to a very high precision rate, 3 delta. So what we do is we actually we use 2 stations. We point both of the stations at the spacecraft itself. Those stations are, of course, one will be located, let's say, in Madrid, and one will be located in the US, and we're going, or in Australia, and we're going to use these stations in order to triangulate the position of the spacecraft itself. But at the same time, we use a quasar we listen to a quasar in order for us to basically use it as a baseline for the signal itself. And then you have to use all that radio stuff and then convert it to basically metric stuff. So that was the hardest for me, since I'm used to working with GPSs and other systems that are more, we could say, more advanced.
Right. So the person who asked the question said it's a simple question, but I'm sure it's not a simple question to answer. So with that, I think the time is up. So but some students were asking some more questions about the thruster and about the propulsion system you had. So maybe if you could share that information later. I'll
write it in chat as we go along, so that I don't take from somebody else's time.
Right, thank you. No, actually, you were the last speaker for this part 1, but
okay.
Right, I think there's an important thing that we need to do, which is to take a group photo So everybody, please turn on your camera. If you have a camera on your laptop or PC, please turn on your camera because you want to be in the picture. Yes, yes. So now I can finally see everyone's face. That's good. So, so I'm gonna wait until everybody turns on the camera, and we'll take 2 group photos. Okay, yes. Get ready. Okay. So I'm not the one who's taking the photo, but I will do 1, 2, 3. Okay. So we'll do it twice. Are we ready? 해도 될까요? 네, 하겠습니다. Okay. Okay, I'm going to count. Okay. 1, 2, 3. Everybody smile. All right. Okay, let's do the second one again. Already? You know, I think if you are by yourself, it's okay to take off your mask. All right? Okay, the second one, let's go. 1, 2, 3, smile. Good, thank you. Thank you. So, Mr. Hussain, thank you very much for your presentation today, you know, and thank you for leaving your email address with us. And maybe Dr. Kim, if you could also share your email address with the students, I think, you know, they may give you more questions to answer. And so let's give a big applause to both of our speakers, even though they may not be able to hear us. Thank you so much. And with that, we'll finish the first part of today's program. But students, please, you should come back within 10 minutes. So at 10:45, we will be starting with the second part of today's program, which is Korea-UAE Young Astronaut Challenge. So I guess the Korean students will be talking about the sounding rocket challenge they have. So everyone, thank you so much. And students, please come back for the second part. Thank you. And thank you, Yak, for organizing this program. Thank you.